Hey guys, in this video we'll show the agreement of the line source solution for the diffusivity equation and the dimensionless diffusivity equation itself. So in essence, this is what we are trying to show. So the line source solution in dimensionless form is PD R sub D TD is, so this is equal to negative 1 over 2 EI, so this is the EI function over here, negative R sub D squared over 4T sub D. So this is the dimensionless form of the line source solution, and we need to show that this agrees with the dimensionless diffusivity equation, which is 1 over R sub D dou over dou R sub D R sub D dou P sub D over dou R sub D, which is equal to dou P sub D over dou T sub D. So we just need to show that these two agree. So now, first let's have a look at what the EI function is, just for clarification. So the EI function is defined as follows. E negative U over U du. Now let me just check the symbol. The symbols are right or not. It's a negative x here, so yeah. So this is the EI function. This is what it is. But anyway, this is what we need to show. We just need to show that these two agree for this video. Alright, so now how can we solve this? The first step is we need to know something known as the, so for this one I'll use a different color, I think. Maybe I'll use green. So we need to note of something known as the fundamental theorem of calculus, and this is also known as aka Leibniz's integral rule. So let's go ahead and show how we can actually get the fundamental theorem of calculus. It is actually a restatement of the chain rule. Okay, alright, let's go. So let's define a function capital G of x, which is equal to an integral between the bounds of lower bound of fx and upper bound of h of x of g u du. Okay, now let's also define another function gamma of x, which is equal to the integral from 0 to x of g sub u, the g of u du. Okay, now I want to rewrite g of x in terms of gamma x. So we can rewrite g of x in terms of gamma x. So how can we do this? And also the reason why we're doing this will become clear in a while. So first of all, we can rewrite g of x using this in this way. G u du subtracted by 0, and here we have the lower bound, which is f of x, g of u d of u. So this is just one of the facts of this is just like a fact of integration, that you can rewrite things in this way. Now this looks awfully familiar with something, don't you think? So if we look at this, these, and also this, notice how it starts with a 0 and ends with something. Starts with 0 and ends with something over here. So now gamma of x starts with 0 and ends with something at the top here as well, and has a gu du. So if you're sharp, you can notice that we can rewrite g of x in terms of gamma x. So let's do this. G of x is equal to, and actually I'm going to use white for, or maybe I should use green. You know what? Let's use green since we're already using green. So g of x can be rewritten as, I'm going to open some brackets here, and I'm going to open some brackets here. I'm going to put a dot here. So this is equal to a composition of gamma and, where's the pen? So gamma of h and gamma of x. And this is a composition of x. Okay, so we have basically just rewritten g of x in this part as this. We've just rewritten it in this way, and now we can apply the chain rule. So we have g prime of x. Now that is equal to, so if we apply the chain rule, what we'll get is, first we will take the derivative of the outside composition, then the inside composition. Okay, so we have, gamma prime of, so inside we will just have a hx, and outside that we will have a h prime of x, and this is subtracted by gamma prime of fx, and outside we have f prime of x. Okay, now also recall that g prime of x can be rewritten as dou over dou x g of x, which is the same as dou over dou x. Now substituting back the definition of g prime of x, which is this bad boy over here, from lower bound of fx to the higher bound of hx g u du. Okay, great. So finally we can write g prime of x is equal to dou over dou x. So it's just basically what we wrote at the top over here. So we can write that as being equal to, using in this form. Okay, so we can rewrite that as being, so now let me pick the right colors for this. Okay, so we will have g open brackets h x here, dou over dou x minus g f x dou f x over dou x. Okay, so what did we just do here? So what we did here was, we just took, to summarize, we defined two functions, and we redefined g of x in this way, which is perfectly valid, which allowed us to redefine g of x in terms of capital Gx in terms of gamma x, which allowed us to rewrite it as a composition function, and after which we applied the chain rule onto it. So we showed that the g prime of x can be rewritten as in this form, which can be rewritten in this form, which obviously, going circularly, is equal to this. So now if this is equal to what we have over here, then we can restructure everything. So we know what gamma prime is, and we have h prime. Okay, so yeah, this is the fundamental theorem of calculus, and it just states that an integral can be differentiated and computed as a difference of two products and is a restatement of the chain rule. Alright? If you're not convinced with my working out, which is, to be fair, not rigorous in any way, then you can look it up online, and there are much better resources. I just wanted to introduce this theorem so that we could move on to actually solving this question. Okay, so again, back to the question. We have the statement of the diffusivity equation, which was negative 1 over 2 EI negative R sub D squared over 4 T sub D. Now we can actually just rewrite this in terms of the EI, the integral exponential, in this way. And here we would have, was it E negative U over U du. Okay, so we can just rewrite it in this way. And the reason why we want to rewrite it in this way is because we can actually apply the fundamental theorem of calculus in order for us to solve the question. So y, again, I'm going to rewrite the definition of the diffusivity equation. So dou p over dou r sub d is equal to dou p sub d over dou t sub d. So we have a dimensionless pressure term here, and we have some dimensionless pressure derivatives over here. One in terms of dimensionless radius and one in terms of dimensionless time. Okay, so let's actually get to it. We'll start with the left hand side first. So starting with the left hand side, we can use the fundamental theorem of calculus to write the following. Dou p sub d over dou r sub d is equal to dou over dou r sub d. Alright, and we have the 1/2 over here. I'm going to include the 1/2 in the integral for the moment. E to the power of negative u over u du. So we can rewrite it in this way, and by using the fundamental theorem of calculus, we can actually split this apart. So the 1/2 can just come out. Dou over dou rd stays over here. So let's open them up. So using the fundamental theorem of calculus, we have, at the very first part, we have this term here, the integrand, substituted with a negative over there. So we will have e to the negative infinity over infinity multiplied by the derivative of our top bound, the dou of infinity over dou of rd, which is what we have on the outside here. And this is going to be subtracted by e to the negative r sub d squared over 4t sub d over r sub d squared over 4t sub d multiplied by dou r sub d squared over 4t sub d over dou r sub d. Okay, so this is the fundamental theorem of calculus. And now, how can we simplify this?